This is lesson 4.3, Riemann sums and definite integrals. We've talked about Riemann sums in section 4.2, where we talked about area. And we talked about integrals in section 4.1, where we talked about indefinite integrals. So now we're going to take two things that seemed as if they were not connected very well and kind of bring it back around and see how they're connected. Remember that with the integrals that we did antiderivatives. And with Riemann sum, we talked about area. That's a parenthesis, not a area. Okay, so we're going to talk about how do area and antiderivatives end up to come together. So first I'm going to give a little bit of history, and this is important information, but nothing you need to write down as yet. First of all, a lot of things about calculus are attributed to Isaac Newton. And notice Newton lived in 1642 to 1727. Well, Newton, to me, was just a genius, and he just really got a lot of stuff. He understood it. He understood calculus. He understood the idea of approaching infinity or approaching infinite amounts. And some of those amounts were infinitely small. But he just got it. Newton just basically got it. He figured it out, and he used it for the purpose of physics. He was not so much a mathematician, he really was a scientist. But he needed that math, and so he figured it out. At the same time, around the same time, we have Gottfried Leibniz. And Leibniz was much more mathematician than scientist, and he spent a lot more time on notation and principles and rules and properties. And so we actually use a lot of his notation, which was actually very cleverly done. So he and Newton are kind of co-credited for being the discoverers of calculus. Well, now we just started talking about Riemann. And you might would think to yourself, well, Riemann must have been working at the same time. But if you take a look at these years, Riemann was 100 years behind Newton and Leibniz. And so when we look at calculus, it's not as if Newton invented it or discovered it or developed it, and then we moved forward from there. Newton used it, and then mathematicians came along and defined some of the definitions, some properties, some of the things that we're going to use. So today we're going to talk about how did this all come together, what was Riemann's part in this, and we're also going to talk about how did we use these properties for integration. So the last thing we talked about was area, and we used rectangles. And so Riemann is really kind of the one who is credited with describing it this way. And so when I think Riemann, I think rectangle. So let's just start from the beginning. If I took this area, I'm going to do the endpoints from A to B. And that was not very good. Let's just say I wanted to make one giant rectangle and say this is my approximation of that pink area in there. Is this a great approximation? And hopefully you would say, no, that's a horrible approximation. Who wants to have that much error? Okay, so what about if I took my two endpoints and divided it in half and I made two giant rectangles? Is that a good approximation? And you would probably say no, but it is better. It's better than what we had. Okay. Well, what if I said, let's break those sections into sections, and now we'll have 4 rectangles. And you might say that's a lot better, but look, we still have a lot of error. So then I would say to you, that's very true. Let's try something else. What if we broke it into 8 rectangles? How would that be? And hopefully you would say that is definitely better. Still getting better. Not there yet, but we're definitely getting better. Still got some error. So hopefully you can kind of tell where this is headed. What if I broke each of these into 16? And then what if I did it again and did 32 rectangles? And then maybe I did again and did 64 rectangles. Maybe I did again and again and again and again. What if I had so many rectangles that you could hardly even tell where the lines were to know how many rectangles there were? Would this be a good approximation? And hopefully you are going to say to me, yes, if you had enough rectangles, that would be a very good approximation. As a matter of fact, if you had enough rectangles to start at the beginning and go to the end, that would be perfect. So how many rectangles would that take? Well, it would probably take an infinite amount of rectangles. And we've talked about infinity before, and hopefully you remember, when did we talk about infinity? We talked about infinity in terms of limits, okay? So if we could approach an infinite amount of rectangles, we would have a very good area. As a matter of fact, if we could approach an infinite amount of rectangles, we would probably have the perfect area. So how does this all connect? And again, this is not something that you're going to have to memorize, so just kind of follow along as we go. All right, so I want my limit to approach infinity. But what is this that's approaching infinity? It's n, and n stands for the number of rectangles I'm going to have. We also call it the number of subintervals. And we're talking about the area of a rectangle. So we've been talking about length times width. And we took those lengths and we took those widths and we added them up, which is what creates a sum, or the summation signal. You may notice sigma means summation. So basically we're taking the limit of the sums of these areas, okay? So now I'm going to change the notation a little bit. I still have the limit as n approaches infinity. It's still going to be a sum, but now let's take length and width and turn them into f of x and delta x. Delta x would be my width, because when we go, as we're going across the page trying to find the width of each rectangle, we were using the x distance. And then f of x would be my L, because to find the length or height of each rectangle, we used f of x to get that point. So now we have the limit of the summation of f of x delta x. Okay, so remember, still have sigma, we're still adding up areas. All right, so it turns out that this summation is going to approach some number, and we're going to call it S sub n. That's just, it's called a partial sum, but we're just going to say for now that that's our value. It's our sum value. As long as n is approaching infinity, we're taking the limit of this sum as n is approaching infinity. Well, interestingly enough, when you take the limit of a sum, it creates an integral. And the integral symbol is a stretched out S, because it's a summation. So if we stretch this out, we have an integral, and we know that it was f of x delta x, so we're going to say that's f of x dx, and we're going to put a beginning point and an ending point. So now this is called a definite integral. We have limits of integration. The a and the b are called limits of integration. We have our function, our f of x, and then remember d of x came from delta x, and so when we did integration, that kind of disappears. Here's why. If we looked at the area of these rectangles, if the number of rectangles is approaching infinity, then the width of those rectangles should be approaching 0. So this d of x is kind of like it's approaching 0, and it's a negligible amount. So when we integrate, that dx gets to go away. Okay, so all of that is leading up to show you how are we going to do this. So here's your first actual example. So we're going to do this with a geometric method. We are going to, next lesson in 4.4, we're going to see how to do all of this integration by ourselves, by hand, no problems. But for now, we're going to still go ahead and look at it geometrically. So what are we looking at here? Well, 4 dx, that means my function is 4. The dx is negligible, remember. So I'm going to draw f of x equals 4, which is a horizontal line. And we want to go from 1 to 3. So these are x values. So when x is 1, and x is 3. And then I'm going to draw, you guessed it, rectangles. I'm just going to make some straight lines going down because those are my boundaries. So this area right here is officially a rectangle. So the area of a rectangle is length times width. Our length is going to be 4. Our width is going to be 2, because from 1 to 3 it's 2, and this height right here is 4. So we get 8. That's the area inside this picture. But it's also the answer to this integral. What is the integral of 4 from 1 to 3? It's 8. That's a geometric method. We're going to do another geometric method. This time we're going to use the square root of 4 minus x squared. This is a semicircle. It might not immediately pop out to you until you see that this goes from -2 to 2, which I gave too many spots. But we're going to go from -2 to 2. So it's going to be half of a circle. Not a very well drawn circle, but that's what it is. Okay, so what's the area of a circle? Pi r squared. And in our case, we only have half of a circle that's above the x-axis. So we're going to divide by 2. So what's my radius? Well, the radius of this, if that's the center of my circle, the radius is 2. So pi times 2 squared over 2, which is 4 pi over 2, which is 2 pi. So that's the area under the curve above the x-axis, but it's also the answer to this definite integral. Now, like I said before, I'm not showing you the calculus method just yet. That's going to be in the next lesson. But this is the geometric representation that we're actually going through to get these amounts. So that's how the area and the integral end up relating to one another. Okay, so with these definite integrals, we have to use lots of properties. The properties are really important because if you don't know how to do the integral yet, you definitely need the property. And then, of course, when you get down to the AP test, they love to test you in ways where you don't actually have a function. So let's look at a couple of properties. The first one says, if I'm trying to integrate f of x dx from a to a, then my answer is going to be 0. Hopefully that's kind of makes sense, because if I start at A and I end at A, have I covered any area at all? No, so it's 0. The second property is, what if my integration limits, my limits of integration, are backwards? It's supposed to be A to B, moving from left to right, but this one's going from B to A, moving from right to left. Well, that just means that the answer is going to be the opposite of what it normally would have been if this had been written in the correct direction. So if my limits of integration are switched, then the answer is just going to be opposite what it would have been to begin with. Alright, the additive property of integration is probably the most important property. It says if I have an integral from A to C, I can break it into two integrals from A to B and B to C. Now, that's important because sometimes we may know this part and may know this part, but we need to discover this part. So if we use this property, we can plug in the parts we know, and since it's an equation, we can solve for the parts that we don't know. So if we have an interval from A to C, we can break it up into two intervals that, as long as B is between A and C. Okay, two more properties. Pretty straightforward ones, though. This time I have a constant in front of my function. Constants are not affected by the integration, so we can just take them out, put it out front. So this is now k times that integral. And then the other one that we've actually already looked at and used a little bit, if I have f of x plus g of x, I don't have to add f and g first. I actually can separate them and get each integral and then add the integral values. So if it's easier to do separately, I can do them separately and then add them together instead of having to add it before integrating it. Okay, so how are we going to use these properties? If I give you a problem that says you're given the integral of f of x dx from 0 to 3 is equal to 4, and the integral of f of x d of x from 3 to 6 is equal to negative 1, how can I find these other things? So here's what we're going to do. Part A. If I need to find 0 to 6 f of x dx, how can I find that? Well, 0 to 6 is the same thing as 0 to 3 plus 3 to 6 f of x dx, f of x dx. That's that additive property we just talked about. So if I know 0 to 3, which is 4, and I know 3 to 6, which is negative 1, then I know the integral from 0 to 6 of f of x dx equals 4 plus negative 1, which is just 3. So I use the additive property there to get a solution. For part B, if I want to find 6 to 3 of f of x dx, well, you know that that's just the opposite of 3 to 6 f of x dx. And in our givens up here, we know that from 3 to 6 f of x dx is negative 1, so I have the opposite of negative 1, which is going to be just positive 1. And then the third part of this problem is asking for 3 to 3 of f of x dx. And I love this property because the minute you see it, you should know the answer. If we start at 3 and we end at 3, we haven't gone anywhere, and that solution, or that area, or that integral is going to be 0. So that's the type of problem that you're going to see in this homework. The assignment is page 279, 23 through 43 odds. You can work on that in class, and you can get help from me if you need it.